Hello everyone, you are welcome to this channel. Today we shall be dealing with numerical methods for solving differential equations. Often we solve differential equations using analytical method, but we can encounter differential equations that are difficult to solve or are very complex, and in that case numerical methods make our job easier. Let us see a differential equation that looks like this, and we are given the initial condition to be this. When we want to solve it numerically, we are looking at the solution yx for this differential equation at different position of x. Unlike the analytical method that gives us a formula to always find x at wherever we desire, in numerical approach, we look for specific position of x. So let's assume this is the curve of the solution, and we are given the initial point x naught. We are given is y solution, our y value as y naught. So our desire in numerical method is to compute the next value of y at x1, which will be equivalent for y at y1, and the next one is to compute it at x2, which will be equivalent to y at y2. So the distance between each of these steps is h. So that's what we call the step size, h. It can be 0.1, 0.2, 0.01, and so on. So the method or the concept that really gives us the expression for this method is called the Taylor's series. Taylor's series. And it is expressed like this. To find the next y in a series is equal to yx plus h y prime x plus h squared over 2 y prime prime x, and so on. So, and if you look at the step size h, if you choose it to be very small, very small, it means the higher power of h will become very insignificant, and will make the whole term here to be closer to 0 because the h is very small. So as a result of that, we can have an approximate value for the series to mean that y in the y at x plus h position is equal to yx plus hy prime x. So this is the approximate value when our h is chosen to be very small, and it can be expressed as this, that is the next value of y equals to yn plus h y prime at xn, or yn plus h function of xn yn. So this method is called the Euler method. That is, this approximation is called the Euler method. Let's see how to apply this Euler method. So example for Euler method. So assuming we are given to solve the differential equation y prime equals to x plus y, and we are given the initial condition to be this at 0, and we are also given to take the step size of 0.2. So to solve this, we have to, or the solution here is, we have to use the Euler's expression, which is what? Yn plus 1 equals to yn plus h function of xn yn. So in this case, our function of xn yn is equal to this. So, and we already know our h to be 0.2 plus 0.2 function of xn yn. Let's put the function directly, which is what? Xn plus yn. So that is how to find every step of our solution y at every position of x. So Let's set up a table for this. We can have a table like this. Let's be counting the step with n and our xn as well as our yn. So initially, at the first step or at the initial step, at x equal to 0, we have our y equals to 0. So in order to get our next step, at xn plus 1, you remember, is equal to xn plus h. So it means we have to add 0 plus 0.2, making it 0.2 here. And our yn, you remember this, is what? Our yn is equal to yn plus 0.2. So let's write it somewhere here. Our yn is equal to our yn plus 1 is equal to yn plus 0.2 xn plus yn. So that means to get our y1, what do? Our y1 is equal to our y0, which is what? 0 plus 0.2. Our xn, x0, y0. That will be what? 0 plus 0. And that means our y0 equals to, our y1 equals to 0. When we go to the next step, our xn becomes 0.2 plus 0.2, making 0.4. And our y2 at that point is equal to y1 plus 0.2 x1 plus y1. And what's our y1? 0. And plus 0.2. What's our x1? 0.2 plus what's our y1? 0. So that will give us what? Y2 equals to 0.04. So this gives 0.04. So those are the other values at other positions of x. So that is all about the Euler method. Let's look at another method called the improved Euler method. So the improved Euler method has the following step or algorithm. So you determine the next x by this method. Then there are some auxiliary steps that we need to follow. We have to calculate k1, which is just like Euler, but when we are calculating k2, we are calculating Euler, but instead of xn, we are calculating it at initial, the next xn, which is adding the step size to the xn. The yn becomes yn plus the k1 of Euler. So that's the difference. So with that, we can now calculate our next solution, y, using the formula shown. So let's see the application of the Euler method, the improved Euler method to the last differential equation we saw. So in that case, this is the differential equation, y prime equals to x plus y, and it has the same initial condition. So the solution using the improved Euler will now be, we need to calculate our k1, which is what? 0.2, our xn plus yn, just like the Euler case, and our k2, which is 0.2. You remember the formula, hf xn plus 1 yn plus k1. So it will now be xn now plus 0.2. That now stands for xn now in the k2 step, plus yn is no more ordinary yn, but we have to add the k1 to it, which is this. So we add this k1 to it. So with that, we can now generate our next y position or solution, which is yn plus 0.2. Remember the formula, which is half. So half with this 0.2 divided by 2, 2.2 xn. So we have to simplify all of those additions, plus 2.2 yn plus 0.2. And finally, we are going to get something in the simpler form as follows: yn plus 0.22 xn plus yn plus 0.2. 0.22. So when we apply the same procedure as in Euler, we are going to have something like this. Our n, xn, and yn. So remember, this is 0, 0, 0. So if we get this one, which is 0.2 in this case, our y1 will be, remember the formula, yn plus 0.22 stuff. So our yn, so our, remember our yn plus 1 equals to yn plus 0.22 xn plus yn plus 0.02. So it means our y1 will be equal to y0 plus 0.22 x0 plus y0 plus 0.02. So it means our y1 equals to 0 plus 0.22. What's our x0, y0? 0 plus 0.02. And that gives our y1 equals to what? 0.02. So here will be 0.02. So the next step, when x is equal to 0.4, we are going to have the following. So those are the remaining values of y as we calculate or we follow the procedures. So I hope the steps are clear. So you can send your comment in the comment section, and make sure you subscribe to the channel by clicking the button below. Thank you.